Okay, thank you. So, so as I said, I am a PhD student. I was a PhD student 3 months ago. So I did this PhD on primordial non-Gaussianity at the University of Paris and University of Paris-Saclay. So on primordial non-Gaussianity, and one of the subjects I've been working on was a relativistic second-order initial condition for simulation of large-scale structure. And this is the subject of this presentation. Most of the results I will present are in this article available in arXiv, and these are all my collaborators. So you maybe know Juliana Damek and Jorge Noreña, who works in Chile with his PhD student Juan Cales, and also there is Clément Stahl, who is a postdoc at the University of Strasbourg. So if you have more questions, you can also ask them if you like. So I like to start my presentation with this picture of the observable universe. So, you know, by definition, we sit here in the center and we are surrounded by the large scale structure. And if we look very far away, we have the cosmic microwave background. And here I represent with this red line here the end of inflation, which is therefore the reheating. And so behind this reheating surface, we have this model of inflation, and this will be the subject of my introduction. So I will just explain what inflation predicts. So you may know Gaussian fields and non-Gaussianities. And then I will speak about the evolution of those perturbations, because of course we cannot observe directly the primordial initial conditions. And then I will briefly introduce the large scale structure, the theory, how it grows, and the relativistic effects. And I will argue that those relativistic effects can be a contamination of some primordial non-Gaussianities, and so we have to model them. And this is why we have developed the code RELIC, which stands for Relativistic Initial Condition Generator for n-body simulation. And I will present some results that we have obtained and that are summarized in this article that I've presented before. And finally, I will conclude. So, you know, inflation has been introduced historically to explain the homogeneity and the isotropy of the universe, because if we draw in the old hot Big Bang model, if we draw the particle horizon for each particle in the observable universe, unfortunately, it does not increase enough to explain the homogeneity. However, if we have a phase of accelerated expansion before the reheating surface here, so the second derivative of A is positive, this particle horizon becomes huge. And so at the end of inflation, near the reheating surface, the particle horizon of each particles are larger than the observable universe. So it explains nicely the homogeneity of the universe. You know, to explain this homogeneity, we need at least a growing factor of exponential to the 60, which unfortunately leads to an empty universe. So you have an homogeneous and isotropic universe, but it's empty and cold. And so any good inflation model has to end with a reheating period, which corresponds to this period where the fields that are acting during inflation, eventually one, but also it's possible to have more, they will decay through a perfectly unknown mechanism into all the particles that we know are filling the universe today. So the baryon, the photon, the neutrino, and the cold dark matter. And the very nice thing about inflation is that, so it predicts the homogeneity and the flatness also and the isotropy, but it also generates small perturbations because of the quantum fluctuation of those fields that will be transferred through this decay into perturbation of density and velocity into all these particles. And those perturbations are the seeds of the CMB anisotropies and the large-scale structure formation that we observe later. So one of the important characteristics of those perturbations is the Gaussianity of those perturbations. So this is, for example, a Gaussian field. So this is a primordial curvature perturbation. And what does it mean that this field is Gaussian? It means that if you go in Fourier space, for example, so you have a real part and an imaginary part. And so each of those numbers here are drawn from a Gaussian PDF. And since we are talking about perturbations, those Gaussian are centered on zero, and the only number that you need, therefore, to characterize this Gaussian is this standard deviation. And the nice thing is that this standard deviation function, at least the square of this sigma here, is proportional to this very important quantity, the power spectrum. And the power spectrum can also be obtained by Fourier transforming the two-point correlation function of this Gaussian field here. We could also compute higher order statistics, like, for example, the three-point correlation function. And in the three-point correlation function in Fourier space correspond to the bispectrum, which is this function here, which now depends on three different variables, K1, K2, and K3. Given this formula here, if you assume homogeneity and isotropy, you see that K1, K2, and K3 have to form a closed triangle. So we always talk about counting triangles in the sky. And for Gaussian fields, this function here, the bispectrum, has to vanish. So this is nice because if you now consider non-Gaussianities, for example, you have here deviation from Gaussianity in the PDF, this function can be non-zero. So the bispectrum is really a clean probe of deviation of Gaussianity, so of primordial non-Gaussianity. And this is one of the reasons it's very interesting to look at it. So this is here a summarize of all the prediction of inflation. I said it predicts perturbation, but more importantly, it predicts the statistics of those perturbations. And so you can compute within models of inflation the two-point statistic, therefore the power spectrum of those perturbations at the primordial time, so right after the reheating surface. And so you obtain in the slow roll standard single field model this kind of power spectra where you have here an amplitude, AS, and NS, a deviation from scale invariance. So if NS is equal to 1, this means this power spectrum, this field here is perfectly scale invariant. And if it is different from 1, it's not scale invariant. And one of the prediction of single field inflation in the slow roll regime is that NS is very close to 1. So NS minus 1 has to be very small to compare to 1. And you can also compute higher order statistics, so the bispectrum. And it turns one of the important shape that is generated by inflation is the so-called local shape that you probably all know. So this is this formula here where you have the amplitude, FNL, and the power spectrum here. So this is here the same power spectrum of the adiabatic mode. And you know, the bispectrum is a function of three different variables, so it can be a bit difficult to represent. So one of the possibilities to plot this function is to fix one of the variables. So for example, we can fix K1, and then we plot the bispectrum as a function of K2 over the fixed K1 and K3 over the fixed K1. So this is here what you see in this plot. In the x-axis, you have K3 over K1 and K2 over K1 in the y-axis. And now you see each point in this triangle corresponds to a given triangle configuration between K1, K2, and K3. So you have here, for example, in this limit, the folded limit where the modulus of 1 is equal to the sum of the modulus of the two other modes. You have here the equilateral configuration, and you have here the very important squeezed limit configuration where one of the modes is very small compared to K2 and K3, for example. And it is very important because you see that this local shape has a peak in this limit, which is a signature of primordial non-Gaussianity and more importantly of multi-field inflation. Why this? Because it has been shown that if you consider only 1 degree of freedom during inflation, and with only this hypothesis, you can show that the amplitude of the local shape is of order ns minus 1. And remember, we said that ns minus 1 has to be very small compared to 1. And indeed, it has been measured with the Planck collaboration, for example, as being of order 10 to the minus 2. So it's indeed very small. And so FNL has to be, if you consider single field models of inflation, of order 10 to the minus 2. Therefore, this peak here in the squeezed limit of the bispectrum, if you consider single field inflation model, is suppressed by this 10 to the minus 2 factor, which means that if one day one measures large non-Gaussianities, and by large I mean larger than 10 to the minus 2, therefore, this would probably mean that all single field inflation models would be ruled out, which make this squeezed limit of the bispectrum a very powerful probe of inflation. Now, so we talk about, we are only talking now about the primordial initial conditions, so right after the reheating surface, but of course we cannot observe directly those primordial initial conditions. We can only see the CMB or the large-scale structure, later things. So we have to care about the evolution of those primordial initial conditions. So the first thing you want to do, of course, because we are looking at very small perturbations. So the first thing is to look at perturbation theory. And first, so you can linearize your theory. So this is, for example, the 0,0 Einstein equation linearized, which is basically the Poisson equation. You see, if you forget about those relativistic terms here, you have simply here the Poisson equation. And the nice thing about those linearized equation is that they follow a translation invariance, which means that in Fourier space, all modes are decoupled. So you can basically write this equation as a function. So with fields in real space or in Fourier space, and it has exactly the same writing. It's exactly the same equation. And this means that basically all fields, so I here can mean phi or delta, at a given time t and for a given mode k, can always be written as a deterministic function, which we call the first order transfer function, which only depends on the modulus of k, because we are isotropic, and which account for the time dependence of your field. And you have here the product with the curvature perturbation. So it's a stochastic part, which we usually take to be the primordial initial condition. So here the stochastic curvature perturbation. And you see that if you replace in this equation by for each field the corresponding first order transfer function and or the curvature perturbation, this stochastic part will simplify, and you only have a deterministic equation to solve for the transfer functions. So now let's see, if you start with a pure Gaussian field, okay, you neglect the primordial non-Gaussianities. This is what we can do in single inflation model because they are small, the non-Gaussianities. So you start with non-Gaussianities with a pure Gaussian field, and you consider only the linear propagation of the theory. Then your field will always remain a Gaussian. Okay, if you start with pure Gaussian, only linear theory, your field always stays a Gaussian, and the only thing that changes is the standard deviation of this Gaussian. So standard deviation, remember, is related to the power spectrum, and so you can compute that at any time t, the power spectrum can be computed by multiplying this first order transfer function squared by the primordial power spectrum, which can be the power spectrum of the curvature perturbation, so the prediction of inflation. Now, if you start from pure non-Gaussian initial conditions, so this means that you can have a primordial bispectrum, then your primordial non-Gaussianity will be linearly propagated through the cosmological history, and you can reconstruct at later time those primordial non-Gaussianities. So thanks to this term, so you see at a given time t, the bispectrum takes this form here, and thanks to this term, we have access to those primordial non-Gaussianity, and we can have constraints. The local shape non-Gaussianity, for example. So remember, single inflation predicts FNL of order 10 to the -2, and this is here a brief summary of the constraints we can have of FNL. So this is here the Planck collaboration constraint on FNL, which is the best we can have. We have today. So this is FNL equal -1 plus or -5. So you see that we are still far from this limit, and it's still compatible with 0. So the initial conditions are still compatible with Gaussian. And in the future, we will have a lot of, and currently we have a lot of large-scale structure survey. For example, last year, we had the first very strong constraint on by the SDSS collaboration with EBOS. So by looking only at the power spectrum of the galaxy bispectrum on the galaxy distribution, we had this constraint. We can obtain this constraint FNL equal -12 plus or -21, which is only by a factor 4 with Planck. So it starts to be very powerful, and in principle, the large-scale structure is a 3-dimensional object. So in principle, we have access to much more information than in the cosmic microwave background. And so in principle, this constraint can be improved by looking at the large-scale structure. And the forecast for Euclid and Spherex and SKR are very encouraging. So For example, with Euclid, we could obtain a standard deviation of FNL of order 1 and even of order 0.1 for spherics and SKA. So you see, we start to be close to this limit here. And so maybe one day we will be able, with those experiments, to exclude all significant inflation model. Of course, general relativity is a nonlinear theory. And so in principle, you could also look at higher order propagation. We only looked at the linear propagation for the moment. We could also expand the theory at second order. So we look at the quadratic evolution. So this is now the relativistic Poisson equation that I showed before, but expanded at second order. You have here on the left-hand side the exact same relativistic Poisson equation as before, but now on the right hand side you also have quadratic terms, so phi squared, gradient phi squared, and so on. And now let's see if you Fourier transform this equation, what happens. So basically all the quadratic terms here will take a very particular form. So for example, if you Fourier transform this term, it will become a convolution integral of K1 and K2, some kernel here, which depends on the operators, and therefore in Fourier space on K1 and K2. You have the fields evaluated at K1 and K2, which you are integrated over, and you have the direct delta function here. Now, the last term, it's exactly the same thing. You have a convolution integral, a kernel, the fields, and a direct delta. So in general, very general, you can always express at second order fields at a given time t as the linear propagation as before. So the first order transfer functions times the stochastic curvature perturbation plus a second order term. And this second order term will take always this form. So a convolution integral here, with a second order generic function, which is those kernel, and it can be different for even each field, and the stochastic part here, a multiplication of the curvature perturbation. So I forgot also there is a direct delta function here, but it's not very important. So with this equation, you can compute the bispectrum at a given time t later, okay? And what you obtain is this formula. So remember, this first term, we already had it when we looked at the linear propagation. This is just if you have primordial non-Gaussianity, they are linearly propagated and you can observe them later. This is this first term. But now you have a second term, which corresponds, we call this term the intrinsic bispectrum. It only comes from the non-linearity of your theory. And it means that if you start, for example, from pure Gaussian initial condition, the nonlinear propagation at second order will generate anyway non-Gaussianity this time. And the question I want to ask here is, and we want to study, is if those two terms, of course, in the future, we will measure the total bispectrum, so the sum of those two terms in principle. And so if we want to have a constraint on this term, we don't want that this second term looks exactly the same as this primordial non-Gaussianity. Otherwise, this would mean that you could confuse those two contributions, and you will have problem to interpret your data. So let's see. To have constraint in the local shape in particular, it's very important, as I said, to look at the squeeze limit, because the squeeze limit is where you have this peak in the local shape, okay? And the squeeze limit, remember, is this kind of triangle. You have two large modes, so two small scales, and one small mode, and therefore one large scale. So this is very difficult to model, of course, because you have different scales involved. And so you have two very different physics, which you have to take into account to model this limit of the bispectrum. The first one is, of course, to look at large scales. So if you study the standard perturbation theory, you can look, to simplify things, at the Newtonian limit. So you consider that the cosmological horizon is at infinity, or you look at small scales in Earth, so that you can use the standard perturbation theory in the Newtonian limit. You have no horizon, and you can show within this limit, this standard limit, that at second order, the density of CDM grows like A, the scale factor. You expand your theory at second order, and you can show that at second order, it grows like A squared. So what this means is that if you want to set initial condition for n-body simulation, which you need to model the large-scale structure, which is nonlinear intrinsically, you may want to set at some point initial conditions. And if you consider those initial conditions at high enough redshift, so at early enough time, this second order contribution, delta 2, will decay with respect to the linear solution because it grows like a square. And so you can, in principle, in the Newtonian limit, neglect this contribution if you set your initial condition at early time. Moreover, you can also compute the bispectrum generated by those Newtonian nonlinearities. So this is an example of the bispectrum that you can obtain. And you see that in the squeeze limit, you have no signal. So this is good because this means that if you set that this second term here cannot, in the Newtonian limit, cannot be confused with this primordial local shape. Okay. However, the future large-scale survey will probe a very large volume, and so in principle we will approach the cosmological horizon, and so we will start to see relativistic effects becoming important. Those relativistic effects are always proportional in the equations to powers of h square over k square. So you see, if you consider small scales, k is very large, and therefore this relativistic effect decays. So you have to consider large modes, large scales, in order to have k small and relativistic effect to become important. So now you have a horizon, and now you see that at second order, those relativistic effects will be, so the time dependence of those relativistic effects will be a multiplication of h square with this a square that we know from standard perturbation theory. And it turns out that in matter domination era, the time dependence of this is exactly a. Okay, so multiply h square is proportional to a, and therefore the second order relativistic density here does not decay with respect to the linear solution, and so even if you set your initial condition at very early time, you cannot neglect this contribution with respect to the linear one. And it's even worse because you can also compute again the bispectrum generated by those kind of terms, and you can show that the bispectrum, relativistic bispectrum, if we can call in this way, take this form here, and you see that you have a peak again in the squeeze limit. So this is the worst you can imagine, because this means that relativistic effects in this term here are degenerated in time and in momentum space with the local shape primordial bispectrum. So if you want to have a safe measurement, you have to estimate this the amplitude of this effect and subtract it from the data in future large-scale structure survey. So remember, this is only because you want to study large scales, but you also have two small scales to take into account. So when you study small scales, of course, this is where nonlinearities becomes important, and so this is why, in principle, this second order contribution becomes important. And also at later time, perturbation theory breaks down, and so you have to use n-body simulation, as I said. And since we are studying relativistic effects, we want perfectly relativistic n-body simulation. This is why we use J-evolution, which has been developed by Julian Adamek in 2016. And when you study small scales, of course, you also have to care about radiation, because small scales enter the horizon at early time, where radiation was not negligible and were still interacting with baryon and so on. So in principle, if you want to model the squeeze limit, you also have to solve the full Einstein-Boltzmann system to account for all the radiation, and all of this at second order, because we are studying nonlinearities. So at first order, you have CUB and class, which are well known, and at second order, so it has in 2014, Guido Pettirani developed a song, the second order non-Gaussian code, which is able to solve the full Einstein-Boltzmann system at second order, and we will use this code, which basically is able to compute this second order transfer function, while the first order transfer function are computed by class and CUB. So this is here a summary of this quite big introduction. So what we want to study now is this second order contribution. This is the purpose of our article. We start with pure Gaussian initial condition, and in its basic implementation, G-evolution set only linear initial condition. So it propagates the primordial initial condition by just multiplying, by just using class, so the linear Einstein-Boltzmann equation solver. And at some point, you have to stop and set initial condition. So you just multiply your first order transfer function by some stochastic Gaussian field, and this sets your initial condition. Usually, we use a redshift of 100. And what we want to study here is the second order propagation. So we have to solve the full Einstein-Boltzmann system at second order by using song. And the question is how from this second order transfer function can we compute this second order initial condition from G-evolution? So this is the question we ask in this article, and we try to answer. The main point here is to care, of course, about the relativistic effect, because remember, the Newtonian part, for example, should be negligible. So the problem, basically, if you want to compute in general, okay, in very general, the second order contribution here to the density, it's a very difficult problem because it's very long to compute. All second order fields can be expressed as this kind of integral. Remember, before you had two convolution integral over K1 and K2, but also a Dirac delta function. So here I just use finally this Dirac delta function to only have one integral. And so all fields at second order can be computed with this kind of integral, if you know the second order transfer function, which is given by song. So here you have the Fourier space field of density at second order. And the thing is that you see that for each pixel, so for each vector K3, you have to integrate over the whole grid. Okay, let's say we consider n mode, so the grid is there is n pixels here. So for one pixel in 3 dimensions, you have n cube terms to compute. And so if you want to evaluate everywhere your second order grid, of course you have n cube pixels to compute, and therefore n to the 6 terms to compute. And this is very time consuming to, and n to the 6 is far too large because, for example, on modern computer, for one processor, if you consider 1000 mod, which would be a reasonable large grid, for our study, it would take on one processor 1000 years. So even with parallelization, it starts to be very, very difficult. You would need millions of probably processors to do this within a day. So this is why we have developed the RELIC, so the relativistic initial condition generator, and it will use a hypothesis to neglect the Newtonian part, which is, as we will see, the longest part to compute. So the point is to split. So we define a cutoff scale, okay, which allows us to split the second order grid, Fourier grid here, into a large scale part. So this is only large modes here, and a small scale part. Okay, so you just need a window function with some k lambda, lambda being the cutoff that you use. And of course, we want to account for all the relativistic effects. So the relativistic effects, as I said before, are important at large scales. And this is here the large scales pixels. So we want to compute exactly those pixels because this is where relativistic effects are important. And it turns out that this computation is only n lambda. So n lambda is the number of modes that you are considering here. N lambda cube. So the time complexity of this computation is n lambda cube times n cube. Okay, so now it scales only like n cube, where lambda can be kept small. So this is perfectly computable. Now the problem is the small scale parts. So for each pixels, again, I remember we have to evaluate the full integral here. So the point, the idea here is to write the curvature perturbation. Again, we split it into a large scale part and a small scale part, exactly like the density here. So the curvature perturbation, if you write it as a large scale and a small scale part, you just rewrite this product, you distribute, and you will see that you have three different terms. You have a coupling here between large and large scales. And this computation is only n lambda 6. So you have a power to the 6, but lambda can be kept very small. So this is very, very fast to compute actually. So you want to compute this term, of course, because relativistic effects, again, are important at large scales. Now you have also here a coupling between small and large scales. So this is also very important because remember, we want to be very accurate also in the squeezed limits. And the squeezed limit is exactly this, a coupling between small and large scales, because in your triangle, you have one very large and two small scales. And it turns out that you see you have mostly 0 here. So if you multiply this grid by this grid, you will have mostly 0. And the time complexity is actually only n lambda cube, n cube again, exactly like this computation. So this is also computable, manageable. And now you have this last term here, which now takes into account a coupling between the small scales. And this is exactly the term that is very long to compute because it scales like n6, n to the 6. And this is also where the Newtonian linearities dominate and should be also negligible if you consider early in-house time. So we don't compute this term, okay, because you have no relativistic effect here. This should be negligible at large redshift. And thanks to this approximation, we are able now to compute the second order initial condition for 1000 mode within on one processor within 100 days, which is still long, but if you use parallelization, you can do this within a day or even less. So this is, for example, the result you can obtain. You have here on the left first order results, and on the right the second order initial condition. But this is not the end of the story, because so now we want to verify that the bispectrum of delta 1 plus delta 2 is accurate, of course, because this is what we want, and especially in the squeeze limit. So what we did, simply, we have generated 20 realizations at second order by using Relic. And then we can compute the bispectrum of those 20 realizations. We compute the average and the standard deviation. And this is what you see here in blue. So by the way, this is here the bispectrum in the equilateral configuration. So we fix all mode to the same value k, and we vary this k on the x-axis, and we compare this with the theoretical prediction, which is here in red. And you have also here in black the cutoff scale that we have used. And of course, we expect our approximation to fail once you consider smaller scales, so larger k, than this scale that we use. So this is exactly what we observe. We are accurate here on large scales, and at small scales, it starts to decay and falls to 0. Now let's look at the squeeze limit. So to look at the squeeze limit, one way on one dimension is to fix the two first variables to k1, which is given here, and you vary the last one. So if you look here on the left, you are very squeezed because k here is very small, and as you go to the right, it becomes more folded. And you see we are compatible everywhere. So for this plot here, the upper plot in particular, you see that we are accurate even after the cutoff here. You see the blue and the red are still compatible here. And so this is due to the fact that K1 is smaller than this cutoff, and our approximation is accurate as long as one of those scales is a large mode, therefore smaller than the cutoff mode that we use. So this is accurate everywhere, and if K1 now is larger than the cutoff, we have exactly like in the previous plot, we are accurate in the squeeze limits, but only before the cutoff scale, and after, so we are not in the squeeze limit anymore, but it decays and falls to 0. So now we compute those integral by using, as I said, the Song second order transfer function. But we only have the density, by doing so, we only have the cold dark matter density at second order. And this is only a grid, okay? And to initialize the n-body simulation, we need more than the density. We also need the velocity, we also need the potential and everything at second order. So to compute those quantity, we can use the Einstein equation expanded at second order. And it turns out that the scalar part of the scalar equation, Einstein equation, have only 1 degree of freedom, and this degree of freedom is given by this delta 2. And so you can compute all fields by expanding the Einstein equation at second order, and therefore we have V2, the second order velocity and the second order potential. So now we have grids, okay, with values. This is what we have computed until now. And of course, when you initialize n-body simulation, you want to create particles with given mass and given position, initial position, and then perform the evolution. And so the question is now, from those grids that we have computed, how can we initialize those particles accurately at second order again? So the way J-evolution works in general is that it starts from a homogeneous template. So you can imagine a crystallographic crystal with perfectly homogeneous with given position for each particle, okay? And the way it works is that it will apply a small displacement field to each homogeneous position, okay, to have the initial condition. And then if you have those initial conditions, so you have created, imagine your initial position with your mass, and you could in principle recompute the density grid, okay, that you have injected before, because you know the mass, you know the position of the particle, so you just have to recreate the grid and project all of those particles in the grid. And you can do this fully non-linearly. It's a computation well defined, and you reproject on your grid and you reobtain the density with the hat, okay, which means that you did all of this path before. And what you want, of course, is that the J-evolution rho hat density that you obtain after reprojection is equal at second order, at least, to the first order density plus second order densities that we have computed with Relic. So the way it works, J-evolution does that every day, but at the linear level. So in its basic implementation, it's only linear. And the way it works is that it solves this equation. So this is the solution. Basically, we know what is here on the left-hand side because we know the density we want. We want this displacement field that tells us where the particle should be initialized. And we also know all those quantity, but it's how we, this is here a kernel related to how you compute gradients in your computer. And this is how this is a cloud in shell kernels, okay? So we know everything basically, and you just want to know this, and J-evolution already know how to solve this equation. The problem is that this is a linear equation. And so even if here on the left-hand side, your density is accurate at second order, which is here the case, solving this equation can only provide you the linear density, the linear displacement field, psi, okay? So if you solve this equation, you will have psi1. And now if you, so with psi1, you displace your particle, you fully non-linearly project again on your grid, and the rho hat that you will obtain, the density that the density grid that you obtain after this reprojection, is basically first order terms. So this is what you want, of course, and you will also have first order square terms and cube term because this is here a non-linear operation, okay? And the thing is that Relic, the density computed by Relic, so this is rho1 plus rho2, is not only first order and first order square terms. There are also pure second order piece that you will miss by doing this operation. Okay, here if you subtract, unfortunately, you see that the error between the rho hat and rho1 plus rho2 is of order 2, and so this is we have to do something more. And so what we so we first try to expand, of course, this equation at second order, but it becomes a bit difficult because, of course, we will have a lot of convolution here with those gradients and so. And so after thinking that this is a bit difficult, we realize that we can reuse the same equation. So we first solve it as we did before to have this rho hat, which is accurate at first order, but also it contains squared quadratic terms and cubic terms and so on and so on. And we realize that if we resolve the same equation, but now on the left-hand side, we don't write rho 1 plus rho 2, but we also subtract by this solution that we had. So now, remember, if you subtract this, this is a pure second order terms, where all the quadratic terms are killed by this subtraction. And so now you have exactly a linear equation on the second order terms, and solving this equation again by using the same part of the Gaussian generator will give you, by definition, now the second order displacement field. And now, if you redo again, you displace your particle, but now with Xi1 plus Xi2, you fully non-linearly reproject on the grid. You will have now rho hat, which is first order plus pure second order terms plus quadratic terms. And now if you subtract, your error is of order 3. So you are happy and you succeed. And so this is here the proof that we give in our article that it works at a very high precision. So this is here the first order power spectrum. Of course, at first order it works already very well. After projection and before projection, you see that it's very accurate. And this is here in dashed and solid lines the second order power spectrum before projection. So only by using the relic grid and after reprojection. And you see that the error is of order 10 to the minus 12. So we are very accurate with this method. And note that this method is iterative. So you could eventually, if you want to be accurate at third order, you could so you have, of course, to know your third order densities that you have to compute with, I don't know, ICCUB code. And you can start again, resolve the same equation by subtracting again this rho hat here that you have computed, and you will be precise at third order, and you could start again, first order, and so on. So now I will present this last result. So this is here basically the summary of the pipeline that we have developed, which is in principle fully consistent with regarding the relativistic effect. So Relic use the Song second order transfer function, which solve again the Einstein-Boltzmann system at second order to compute the density field at a given redshift. So basically, usually we use redshift 100. Then by using the Einstein equation, we can compute all the fields we want, V1 and the potential, which are useful to initialize the particles with a given velocity, given position, with this method that I just presented before. And of course, all of this was before only at the initial condition. And we want now to perform the evolution at some point. So what we can evolve those particles until redshift 50. So we want still high redshift, because you will see we want that perturbation theory still hold at this point, because if it still holds, we could in principle also compute directly with Relic this density at redshift 50. And so now, by doing so, by computing this quantity with those different ways, the $1 million question is if those two fields are equal, or at least statistically, are they compatible with each other? And this is what we show in this. So this is the last result that we show in our article. Here in dashed blue, you have the power spectrum, so the second order power spectrum of Relic. So this is here the second order power spectrum. So no G-evolution evolution here. And you have in cyan blue the second order power spectrum after evolution. So with all this way here. And you see that it's quite different. So we are quite accurate at a 10% level in this range here. At small scales, it differs, but we expect this because of discretization error in this evolution. We expect that at small scales, it become a mess. And at large scales, we didn't expect that it doesn't work at all, and this is still an ongoing work. We don't know why we have this big discrepancy. So we also tried to compute, so to do the same thing here, but only with linear initial conditions. So we run Jevolution with linear initial condition from redshift 100 to 50, and we obtain this power spectrum here in gray. You see, it's very close to the cyan. At very large scales, it is even equal. And you see that it's interesting to see that in this region here, the cyan has more power than the gray, okay? And so this is exactly what we see here. This difference only comes from our second order initial conditions. So this is very encouraging, because this means that even after evolution, we still see our nonlinear initial condition, but we still have this big discrepancy here at large scales. And for the moment, our hypothesis is that there is some approximation, some difference between the physics that is solved in Jevolution and the physics that is solved in Song. So here, actually, what we have constructed is a consistency check between a second order Einstein-Boltzmann system solver and an n-body simulation. And this is very nice, because we are able to compare and to test those codes with each other. And it turns out that Song, since it is it's not the only code of this kind, but it's the only very fast code of this kind, and so it has not been very well deeply tested, and so maybe this will provide us a new test that we will be able to find some approximation or something that is different between Jevolution and Song. So now I conclude. So it will be a short conclusion. So I showed in this presentation that I argued that so it's very important to study inflation, of course, and one very important way to study inflation is to look at the squeeze limit of the bispectrum. And the problem with this squeeze limit is that it is degenerated in time and in momentum space with the relativistic effect that arise from the second order evolution from the primordial time to the large scale structure. And so we have to account for this effect. And we must initialize, and therefore we must initialize the n-body simulation at second order. So therefore we have developed RELIC, the relativistic initial condition generator, which by neglecting the small coupling, which is Newtonian, only Newtonian nonlinearities and very long to compute, is able to compute the second order initial condition in a reasonable time, even though it's much longer than the n-body simulation itself. And thanks to the RELIC, we have an accurate bispectrum at large scales and in the squeeze limits, which is what we wanted. And then we have a generalized Jevolution initial condition generator at second order with this iterative method. And then we have looked at a bit at the evolution, but it's still the first result that we present here. And we have shown that at large scale, we still have some discrepancy, which is very encouraging, because this means that there is something to find in the physics that is taken into account in Jevolution and in the second order Einstein-Boltzmann system solver Song. So thank you for your attention.